Welcome to The Explainer. Today, we're unpacking a truly bleeding-edge concept in theoretical physics. We're looking at something called swing surfaces, which comes straight out of a fascinating presentation by physicist Sabrina Pasterski. If you're into exploring the absolute frontier of quantum mechanics and gravity, well, you're in exactly the right place. We're going to decode the abstract math and break it down step by step.
So how do we actually decode the geometry of a flat universe? That is the massive question we're tackling today. For decades, physicists have relied on some absolutely incredible mathematical tools to understand how quantum mechanics and gravity interact. But there's a pretty big catch. Those tools, they were built for a hypothetical curved universe. So how do we adapt our best mathematical framework to work in our actual universe, which is fundamentally flat? It's a real scientific mystery, and it requires some serious mathematical acrobatics.
Okay, so here's our roadmap for the explainer to keep us on track. 1. The quantum gravity playground. 2. Taking the flat limit. 3. The swing surface proposal. And 4. Unlocking the inner horizon. Let's get right into it.
Let's dive in and establish the foundational blueprint physicists are currently using. Section 1, the quantum gravity playground.
Right at the center of this blueprint is ADS/CFT. You can basically think of it as a holographic tool. It's this beautifully elegant mathematical space, a playground really, where quantum information on a lower dimensional boundary perfectly encodes the gravity of the higher dimensional space, or the bulk, inside it. It's arguably our absolute best framework for marrying quantum mechanics and gravity. But, as the name implies, it operates as a theoretical playground. It's a highly controlled, kinda artificial environment.
And that brilliantly illustrates our overarching problem. Think about global ADS. That's our curved toy model. It works so perfectly because it has a natural physical boundary, kind of like the walls of a soup can, where we can just pin our mathematical data. But contrast that with asymptotically flat space, which represents our actual universe. If you scatter particles in our universe, that data doesn't just hit a neat wall. It travels infinitely outward to what physicists call null infinity. So we really need to figure out how to use our holographic tools in a universe where the boundary is just an infinite expanse.
So how do physicists actually bridge that gap? That brings us to Section 2, taking the flat limit. To mechanically get from that curved toy model over to our flat universe, physicists perform a wild mathematical maneuver called taking the flat limit. Imagine you're trapped inside a curved cylinder. If you mathematically stretch the radius of that cylinder all the way out to infinity, well, the curve begins to look completely flat. But get this. By taking this large radius limit, mathematically speaking, you were essentially sending the speed of light down to 0. This creates a bizarre, ultra-local environment at the very edge of space known as a Carrollian theory. Down here, everything is governed by a mathematical framework called BMS symmetry. We're literally zooming all the way in on the light cone until it crunches up into a single line.
But, as you might guess, when you stretch space-time out to infinity, things get weird. As Sabrina Pasterski notes, when you start manipulating these dimensions and tweaking the central charges to force a flat limit, well, there will be the dragons. We are stepping into mathematically dangerous and totally unpredictable territory here. The normal rules are definitely about to break.
Which leads us to the core mystery of this explainer. Section 3, the swing surface proposal. In that curved toy model we talked about earlier, physicists use something called the Ryu-Takayanagi or RT surface formula to measure quantum entanglement entropy. It's a standard, super reliable formula. But when you stretch the universe into that ultra-local flat limit, the standard RT formula just totally fails. It doesn't translate at all. If we want to measure entanglement in our actual flat universe, we need an entirely new approach.
And here is the exact concrete recipe for that new approach. Let's walk through it. Step 1, you take an interval out on that far edge of the universe, on null infinity. Step 2, you shoot in radial null geodesics. You can just think of these as light-like ropes dropping down into the bulk of space. Step 3, you hunt for another geodesic segment that spans the gap between those two ropes, almost like the seat of a swing connecting the chains. And finally, step 4, you mathematically extremize where that seat attaches to the ropes to find the saddle point. That is the swing surface proposal. It's exactly how physicists are calculating entanglement entropy in this flat space.
But remember those dragons we mentioned? To make this swing surface mathematically match the boundary theory, you have to do some incredibly unconventional things. As Pasterski points out, I want to use the word modular flow with scare quotes. It's not going to look normal.
To get the math to actually balance, the proposal requires physicists to effectively flip a sign, taking the difference between left and right moving vector fields. It's a super weird approach that completely defies our standard intuitions about entanglement.
So why do it? What is this bizarre swing surface actually revealing to us? Let's get into Section 4, Unlocking the Inner Horizon.
We can actually map these incredibly dense mathematical tricks straight to some profound physical implications. Because of those light-like ropes, the swing surface pushes the mathematics much deeper into the bulk space than standard models do. Actually, it pushes so deep that it starts probing the inner horizon of a topological black hole. The equations coming from this weird boundary theory begin to perfectly capture the inner horizon vector fields in subscale physics. The real reason physicists are paying such close attention to this seemingly backward, scare quote heavy math is simple. It works. By extending the mathematical map beyond a black hole's standard outer horizon, the swing surface computation successfully reproduces the thermal entropy of the black hole's inner horizon, and it does it from a flat limit calculation. By taking the difference between those left and right moving terms, physicists accidentally stumbled onto a subleading mathematical saddle that unlocks the absolute deepest, most hidden thermal properties of black holes in a flat universe.
But before we wrap up this explainer, I want to leave you with a massive, provocative question. In physics, we expect the inner horizons of black holes to be incredibly unstable. The quantum fields there behave totally erratically. So if this groundbreaking swing surface proposal relies on matching the thermodynamics of an unstable inner horizon, what does that mean for the future of flat space holography? Are we peering into a brand new fundamental truth of our flat universe, or did we just find a really elegant mathematical mirage? It's a thrilling cliffhanger right at the edge of modern physics. Thank you so much for joining me in decoding this source material today, and as always, keep questioning the universe.